Great. Okay, well, let me just go ahead and introduce Professor Kamran Paynabar at the School of Industrial and Systems Engineering at Georgia Tech. Professor Paynabar is the Fouts Family Early Career Professor and Associate Professor. He received his Bachelor of Science in Industrial Engineering from Iran University of Science and Technology and his Master's in Industrial Engineering from Azad University, his Master's in Statistics from the University of Michigan, and his PhD in Operations Engineering from the University of Michigan. Dr. Paynabar's research is both applied and theoretical aspects of data mining and statistical modeling, integrated with engineering knowledge. His methodologies have been widely used in a variety of applications, including aerospace and others. Professor Paynabar is an outstanding teacher. He has been recognized with the Georgia Tech 2014 Junior Faculty Teaching Excellence Award. So with that introduction, I'll turn it over to Professor Paynabar. Thank you.
Thank you, Glenn, for the introduction, and thank you for the invitation. I apologize again for the delay. A little bit of confusion about the timing and stuff. Anyways, I'm glad to be here and present our work. Today, I would like to talk about the topic of the abstract is very specific, which is part of a bigger scheme of active learning and sampling. And I will talk about this because it has some aerospace application. But before that, I want to talk about a big picture about my research and talk about the motivation and problem statement. And I talk about the active learning and adaptive data fusion for efficient testing with a specific emphasis on intelligence sensing for anomaly detection. And then I wrap up with summary and QA. And please stop me if you have any questions. We can do this very interactively. Okay, so what I do, I focus on developing engineering-driven analytics and machine learning and focus for high-dimensional data, mainly high-dimensional streaming data, and the main purpose is to model a system and try to improve it. And how we can improve that? By adaptive testing and data fusion, predictive analytics and prognostics, systems monitoring and anomaly detection, fault diagnosis and variation reduction, and process optimization and control. These are the areas that I actively work and try to marry machine learning and low-dimensional learning with engineering principles and with the applications in engineering problem. The main area is in the manufacturing, but I also work in the healthcare and services as well. Here are some examples of high-dimensional data when I talk about high-dimensional data. So in valve seat assembly process, for example, at each operation, we have a force profile. This is a sensor measuring the exerted force in each operation. In forging, we have a multi-channel signal. So this is a functional data, which is high-dimensional. This is for high-dimensional functional data, because each point in this function can be considered as one dimension. And we have a rolling, basically, a process where the surface of roller is captured by a camera. So we have a video. This is another type of high-dimensional data. And another example would be point cloud. For example, if you produce something, you have a 3D scans, your CMM machine, it creates a point cloud, which again is in high-dimensional. Just one quick question. Do you see my mouse on the screen when I move it? Just want to make sure.
Yes, we can see it.
Okay, that's good. In case I want to point out, that would be easier. So as I said, so what do I do with this process modeling? We do anomaly detection. For example, if you have a surface, here in this example, we have a stress strain heat map, and you can see there are some anomalies with high stress here, and we want to develop methodologies that can detect anomaly in real time, on the fly. Or for process modeling, for example, if you have some inputs in the process and some high dimensional output, how you can create a function, predictive function, that relates this high dimensional input to high dimensional output. For example, in this case, the input could be a scalar, could be a functional data, could be an image, and output could be, for example, a point cloud. So how we can, and you are familiar with regression modeling, but how we can have this high dimensional regression modeling for high dimensional data. This is another topic of interest that we worked on, and how we can use this function both for prediction and process optimization. So what are the best settings for optimizing the process? We do a lot of process monitoring as well. So for streaming data, when you have images over time, you want to basically detect anomalies and identify out of control situations. I work with network data as well. This is an application in finance and also social networks. So if you have snapshots of networks over time, how you can model the networks and how you can basically monitor that. So here is one example of image-based process monitoring that I was talking about in the methodologies that we developed. Let's say this is a basically a simulated data heat transfer process. Let me see if it works first or not. Yeah, it does work. That's good news. Sometimes videos and inside presentation don't work. This is basically what you see here on the left corner, top corner, is the some heat transfer process. Okay, so we simulated using some differential equation, but it's very noisy, as you can see. So what we do, we want to estimate the noise that basically image. At the same time, if there is anomalies, we want to detect it on this panel. And this control chart can do a sequential hypothesis testing to see whether this detected anomaly is statistically significant or not, or in other words, whether the process is in control or not. As you can see, this is very noisy, but we see that this is a heat transfer process, gradually heat transferring, and everything is fine. Suddenly something happens, we can detect it, and the process goes out of control. And the most important thing here is we are doing this in real time. Okay. Again, these are just examples of what type of research I do. I do also research on degradation analysis. So basically, with different types of data, for example, I think that would be something interesting to aerospace area as well. So let's say, for example, in this aircraft engine, you have different types of sensors. Some of them are degrading, some of them are not. With respect to faults, some of them are informative and some of them are not. How you can utilize these multivariate degradation signals to predict the remaining lifetime of a system. So it's basically one example of high dimensional data where we have multiple sensors and each sensor is capturing one data from the system. Okay. Another type of high dimensional data is basically you have one sensor, but the data that you have is high dimensional. For example, in car engine starter degradation, you see that this is basically car engine. Every time that you start, this is the current, and with respect to sampling length, this is the beginning of the start, this is the end of the start process. And if you plot them over time means every time that you start the machine, the car, you will see that there is a degradation. So you have degradation profiles over time. And another example would be image streams. So you have, for example, in this case, we have a rotating gearbox here, and we are using infrared camera to see the behavior of the thermal behavior inside, which is caused by friction. And the question is how we can use this stream of image and based on this degradation, image degradation, whether we can predict the remaining lifetime of the system and whether when this gearbox inside is gonna, bearing inside is gonna fail. That's another type of high dimensional data analysis, and we can use it for degradation modeling and prognostics and estimating the remaining lifetime of the system. All right. As I said, there are different basically problems in the prognostics that we worked on ISY with my colleagues and my students. One is multi-stream signal fusion based prognostics. So basically identifying informative sensors and based on that have a prediction. What if we have very largest data set? Can we have efficient algorithm for estimating the remaining lifetime, which is scalable to large data set? That's another topic that we work on. Another topic which is really interesting to us would be also when you have poor data quality, meaning that you may have some interruptions in the data collection. For example, this is a degradation signal, but what you're observing because of sensor malfunction, because of basically difference in the sampling frequencies, or because you are using a Wi-Fi basically sensor that cannot be captured data with every time, so at every sampling frequency. So for any reasons, you are observing a sparse observation. So you are only observing the red dots rather than the whole signal. Now the question is, can you do prognostics with this sparse data, poor quality data, with a lot of missing the values? And this is another topic we worked on. And as I said, we worked on image streams as well. Okay. So that's basically just like a big introduction of what kind of research I do with respect to high-dimensional data analysis and low-dimensional learning from high-dimensional data. Okay. The second type of research I do is related to active learning, and that's the topic of today's presentation. And what I'm going to do is basically adaptive sampling and active learning. This is a paper now is published, actually. This is by my former student who is now assistant professor in Arizona State University, and my colleague Jiang-Chin. Adaptive framework for online sensing and anomaly detection. So let's look at a motivation here. Sometimes we are talking about the era of big data, and we keep repeating that. But in many cases, including some non-destructive or destructive tests, or some expensive simulation, the data collection process is very expensive and time-consuming. Okay, so in those cases, we cannot have a lot of data. We have limited resources. And what we want to do, we want to make sure that we take advantage of those resources very carefully and try to basically get the most out of this sampling or samples we collect from the system with respect to some criteria. Okay, for example, this is an example of a slow sampling. This is with our former colleague, used to be in Aerospace, and now he's, I think, dean in University of Colorado Boulder, Massimo Rosini. He had a setting for guided wave test, non-destructive evaluation, and basically what he did, he had this, let's say, a specimen, and he had some excitations, and then laser to the basically a specimen, and based on reflection of lasers, he could do some Fu-Yuen analysis and identify basically the area which is under stress. Okay, so based on that, he can detect he was able to detect defects. But what was the problem with this approach? This is a point-based approach, points-based inspection. So for example, he can inspect each part like a locally, and then he has to move on. We have to move on to the next basically location, and the next location, and the next location. So basically it's point-based, and every time you are spending some time to collect data. Okay, so one way to make sure that we detect all the defects and their shapes is also important. Not only detecting the defect, but what is the shape in this defect in this specimen, is to do dense sampling. So basically you can have very small, very fine grids, and you can sample on each grid. But it basically creates a lot of problem, because It's slow and it's time consuming, and sometimes it's very expensive. The same situation in the running expensive simulations. Okay, so when you have expensive simulations, when you want to run it, it's going to take a lot of time. So the question is, can we use an active learning based sampling strategy to learn the governing smooth function with non-smooth feature? If I want to translate that, it would be, can you tell me what is the background and what is the anomalous features in this background with minimal sampling? That's the problem that we want to solve. So instead of doing dense sampling, which requires a lot of samples, we want to say, we want to reduce the number of samples, but sample sequentially and intelligently, meaning that based on the result of previous sample, I decide where to put or where collect the next sample. That's the problem that we are trying to solve. Any questions so far about the problem statement? Good? Okay. All right, I continue. So what is the existing sampling strategies? Let's look at the literature. So one way, as I said, is multi-resolution grid strategy. So basically what it does, they start with the coarse fine grid. So they start with the coarse sampling. So you can see this is a coarse grid. And they collect the sample, all basically points. So the sample here, here, here in each basically square. And after finding a problem in one square, they do fine sampling. So they focus on that and try to do a finer grid inside this square. So this is a multi-resolution grid strategy. So the limitation is not flexible for complex anomalous shape. Okay. Another is called the sequential design of experiment. This is very famous approach in DOE and among engineering statisticians. And they use a function expected improvement. And what they do is basically, with respect to function, they try to collect samples with respect to one objective function every time they want to maximize this objective function. But the problem it has is it tries to improve function when there is no anomalies. So if you have, by a function, in our example would be the background. If you do not have any background, any anomalies, these methods would be able to recover the underlying functional background. But if there is anomaly, they are not useful. So here is one example. As you can see, they can recover the function, but if you have anomaly, they cannot. And there is another one, representative point method, and they basically work with anomaly, but they assume that the anomaly distribution is known. In reality, anomaly distribution is unknown in advance. And basically, this is their methodology, how it works. I'm not going to explain, but what we are trying to do to address those limitations and basically propose an intelligent sampling strategy to quickly locate and focus on anomalous region. It can estimate functional mean, which is background, and anomaly estimation, which basically important to find the shape of the defect if there is any defect. All right. So how our methodology works, it's based on one important principle, which is exploration and exploitation. This is coming from active learning literature. So we want to make sure, if we are doing sampling, we need to make sure we sample all the space, because we do not want to miss an anomaly. So if there is any defect, we want to make sure that we have a space filling design, meaning that we are sampling all the space, okay? And to make sure that we are not missing that. This, we call this exploration. We are exploring this space. On the other hand, basically the exploration, as I said, distribute the points over entire space, make sure no anomaly is missing. But the problem is we cannot get, if we only focus on exploration, we cannot get the shape of anomaly. We can say, oh, we found one point, which has a problem, but we don't know what the shape of anomaly is. On the other hand, we can have focus sampling, which we call exploitation. Basically, when you find an area that there is a defect, you want to have more sampling to be able to detect that the shape of it. Okay, so basically, as I said, dense sampling near anomalous region, and we don't know in advance the anomalous location. And if we only focus on exploitation, we may miss other anomalies in other locations. Okay, so there should be a balance between exploration and exploitation, and that is the main backbone of our methodology. So do exploration and exploitation at each step to make sure that you are not missing any anomalies, and if you find any anomalies, you can identify the shape of it. Okay, so how does it work? We start with initial sampling, and we have a methodology called for some reason the cursor doesn't show up here. Anyways, we use AKM2D. I'll tell you what this is. It says standing for Adaptive Kernel Methodology to do exploration and exploitation, as I said. And every time when we distribute, we identify the locations of the sample, after sampling, what we do is a two-step approach. In the first step, we try to estimate the functional mean and background. And after that, we want to identify the defect, the shape of defect. So that's like how this flowchart works. So let's start with basically this balance between exploration and exploitation. The first thing that we do is a space filling property, or a space filling design. Basically what we are doing, we are using a space filling function. Sorry, let me see if I can let this find a way to see how this cursor works. I'm gonna exit and then come back. Okay, now it works. Okay, that's much better. Okay, so the first part of the function, as I said, there is a balance between exploration and exploitation. The first part is exploration, and we are using a space filling design. What is a space filling design? It means that when you have a sample, you want to fill the space. You want to make sure that all the points are collected. And this is done by this criterion. So basically, we want to make sure that the location of sampled points, which is RK, is minimum from it's a kind of like a max mean operation. So you want to fill the space. And the other one is focus sampling. So the focus sampling is coming from a kernel distribution. So basically what we have here is a Gaussian kernel. So we are assuming that the shape of anomaly is coming from a mixture of Gaussian distributions. Okay, so this is a Gaussian distribution, and this is the probability of coming from this basically cluster. And we add them up, it would be a mixture of Gaussian distribution. It's flexible to basically identify the distribution of anomalies. Not the shape of anomaly, but the distribution of anomaly, where they are located. Okay, so anomalies can be located only in one cluster or could be from different clusters. And this is basically representing a sort of like a different clusters of anomalies and their distributions. So basically what we need to do, we don't know this function in advance. We learn this function as we go and as we sample. All right. And we also have some U, which is kind of like a random sampling. We combine these two, this F function and psi function. And since they have different scales, we try to scale them by using this lambda. And at each time, we want to maximize this function. Okay, so basically what we are saying is the next sample, the location of next sample, is the location which maximizes these two functions together, which means that it guarantees the combination of a space filling design or exploration and the focus sampling, which means that if you have a sample, I want to have more samples around it. So these can give us the principle that we are looking for, which is exploration and exploitation and balance between these two. So the sampling criterion now it's trying to ensure both exploration and exploitation by maximizing at each step, maximizing this function. So at each step, we say the location of next sample is, so this is the locations for potential locations, for example, is the one which maximizes this function. Okay, and that function is exploration and exploitation. All right. And we call this adaptive kernel maximum minimum distance. The max min distance is basically this part, which is space filling design, and adaptive kernel is this part. Why we call it adaptive? Because every time, based on the information that we have from the anomalies, we update the distribution of anomalies. Not only the distribution based on kernel, but also probability of each point being an anomalous point. All right. So there are some theoretical properties. I'm not gonna basically focus on that. Basically, what these theoretical properties said, the take-home message for these theoretical properties are, the first one is guaranteeing that there is no, so two things. The first one is guaranteeing there is no anomaly missing, okay? So the input of this algorithm is D. D is the size of anomaly that you want to make sure that you capture, okay? And this algorithm can guarantee that you are not going to miss that anomaly if you follow this algorithm, okay? That's the mathematically proven. And the second one is, again, ensuring that there is a balance between exploration and exploitation. Okay, I'm not going to go over the mathematical details of that, but let's see if we follow this algorithm, how it performs. Okay, we started with a simulation study. Okay, let's say we have y and we have a mean function, which is the background. This is the mean function. As you can see, it's a spatiotemporal process. Okay, it's not solid background. It has some gradients in the color, as you can see. Then we add some anomalies, and these are anomalous regions. And then we add some noise to generate the data. And this is one example of generated data. Okay, so this is one example of generated data. If you do dense sampling, you can observe this. Okay. And noise is coming from a normal distribution. We have two benchmark methods. One is random sampling. So some people may say, okay, if you want to reduce the number of samples, let's do random sampling. And the other one, which is kind of like a current practice, engineering practice, is the multi-resolution grid. I talked to you about that. So go with the coarse grid, and as soon as you find one location which is suspicious to an anomalous region, then do finer grid around that. Okay, so we want to compare our method with these two approaches. So in this video, this is basically, let me tell you what each panel talks about. This panel here on the right is just the value of the objective function that each time that we want to maximize. So basically, if I go very quickly, that is the G function, that multiplication of these two components. So this right panel here shows the value of the function, okay? And each time we are picking the maximum, all right? This is the performance of our algorithm, shows where we are finding or sampling, where in a space we are collecting data if we use this our proposed algorithm. This is the multi-resolution grid, and this is the random sampling. And the budget that we have is only 250 samples, okay? So we cannot do dense sampling. I let it run. You see that the algorithm detects every time it touches one area, it tries to basically do more sampling around it. You see that? So that's how it works. If you look at the random sampling, this is with 250, okay? Random sampling only can, it misses 4 basically area, and it cannot detect basically the shape. So this is just the location. I'll talk about shape in the next slide. Grid sampling, it based on 250, it only can basically capture the shape of one area, okay? And our algorithm misses only one, basically, with 250 misses one location. But if we increase the number of data, as I said, there is a guarantee for 350, for example, based on the theorem that we have, it can detect all the defects that we have. Anyways, but if you look at something one observation is very interesting. This observation. So you see that there is some false alarm in our algorithm. Okay, so we are doing more samplings in the area that there is no defect. However, this algorithm is just sampling. The second step is finding, based on the samples that you have, try to identify the background as well as anomalous shape, shape of anomalies. And here is the results. So if this video was for 250, but we increased the samples because otherwise grid and random cannot compete at all. So we increased it to 400. And as you can see, this is the algorithm. This is the performance of our algorithm. With 400, it can detect all the anomalies. And you can see the shape are very close, okay? And interestingly, this area that we oversampled as a false alarm, our algorithm, after doing the analysis, it says there is nothing here. So although we did wasting a little bit of samples here, it didn't impact the anomaly detection part, okay? Random, as you can see, can only detect 3 anomalies, but you cannot basically reconstruct the shape. The same thing for grid. Grid can sort of like reconstruct the shape of only 3, but missing the rest, okay? All right, and there we do also have some statistical measures. Basically, we have, you know, like we have accuracy and false positive and false negative. False positive is basically there is a location which is not anomalous, but we mistakenly say it's anomaly, and this is false positive. And false negative is there is an anomaly, for example, here, and we cannot detect it. If you combine these two measures, the false positive and false negative, the basically a harmonic mean of precision, you can calculate precision and recall, and the harmonic mean of that is called F measure. The higher, the better. So if you look at the algorithm that we have for every, like no matter what the sample number is, our algorithm beats random sampling and grid. And something would be very interesting to pay attention to. When we increase the number of samples, we are getting closer and closer to dense sampling. So when you have dense sampling, then this gap is going to close. So for example, if you're from 1,000, you go to 10,000 or 50,000, then there is no difference between these two. So basically, this method is only valuable when you have limited resources. If you do not have limited resources, then that doesn't make sense to use this method. And this is also the exploration ratio, how much we spend on exploration, and the rest would be on the exploitation. As you can see, this is random sampling is completely random, so it doesn't do the exploration ratio is always the same because it's always random. Our method, as you can see at the beginning, I'm sorry, this is exploitation ratio. At the beginning is we are more exploring, and then as we get more information from the anomalies, we do more exploitation. So that's what it means. So at the beginning, more exploration, and towards the end, more exploitation. So time is also important, our algorithm time, because we are solving an optimization problem, and the optimization problem is quite nonlinear, okay? But we found some very nice heuristic algorithms for solving that. And still in each iteration we are solving that optimization problem, remember that. So we can solve that optimization problem in less than 1 second. As a matter of fact, it's 0.0053 seconds on average. And random sampling is definitely, and grid is much less because they don't do any optimization. However, our algorithm is quite scalable to real time. Okay, let's look at this guided wave test. As I said, with the setting is for by Professor Massimo Rosini. Used to be in aerospace at Georgia Tech. And as I said, basically this guided wave test, there is some excitations in this specimen that we have, and then there is a laser beam based on the reflection of the laser. They can identify whether there is an anomaly or not. It's a time-consuming process because it's a wave, so wave goes, and then if it touches a defect, it propagates. So it's a time-consuming process. If you want to do dense sampling, for example, dense grid of 27,000 points, it's going to take 2 hours, okay? And the sample dimension in this case is 600 by 600 by 1.6 millimeter. And we assume that the partial sampling is available. And what we are going to do, we are going to compare the full sampling results with partial sampling. This is the energy map with full sampling, dense sampling, which is 27,000. And if we use some anomaly detection algorithm that is again developed by our group, you can detect the anomalies here. This is the anomaly detected from this image with full sampling with 27,000 points. But if we only use 300 samples, which is around 1.2% of points, okay, then three methods. Our method, AKM2D, random sampling, and grid sampling. So this is how the samples are collected, these 300 based on our algorithm. As you can see, we are covering the whole space, but we have more samples around the defect area. We have a little bit of false sampling here, but again, it wouldn't impact our detection algorithm because it's quite robust to non-defective area. And we have random sampling. Random sampling only touches some points. And grid cannot even start doing basically multi-resolution stage, the final resolution. So our algorithm, the result is this. As you can see, this is random and this is grid. Okay. So if I want to compare it with basically the full scan, this is the full scan result, and this is what we have. Actually, we are doing quite a good job in terms of detecting the shape of it. It's not 100% that for sure. There is some errors always associated with that, but it's not bad. I mean, the shape is similar to the shape of the actual anomalies. And instead of 27,000, we have 300 data points. Okay. As a summary, what we proposed here is an adaptive sampling strategy based on active learning. In the cases that sampling is expensive, it would be either in non-destructive tests or destructive tests, or even in your simulations. So you don't want to run the simulations for all the settings possible. So you have only limited budget. You want to know how you can sample more intelligently. And in this application, the criterion was not only finding the background or mean of the system, or the average of the system, or background in this case, or functional mean, but also identifying anomalous features, okay, some non-smooth features in your function. And we try to basically balance between exploration and exploitation by introducing some optimization and also integrating it with the statistical modeling for defect detection. The part that I skipped here was the part that what we do after sample. So I didn't explain that because, but in the paper we have all the details. So when you have the sample, how you can detect those areas and the shape. So we propose some algorithms for defect detection based on partial observations. I skipped that part. I just showed the result due to the interest of time. But we combine this basically adaptive sampling with this anomaly detection strategy, and based on simulations and real case study, we show the effectiveness of the method. Okay, I'll stop here, and I would be happy to answer questions or take, like if you have any comments, I would be happy to hear that. Thank you.
Thank you, Kamran.
Just to make sure I'm still on, is that right? Yeah. Okay. Yeah, because sometimes, yeah, once it happened, it seemed that I was like off, and I was talking to myself for 30 minutes. So
no,
that was, yeah.
That was good. Thank you.
Okay, thank you.
Yeah, I guess my question is how. So when we talk about spacecraft, we are typically talking about very expensive components and sort of custom designs. I was wondering how you would apply your algorithm to that kind of an application. Like, I guess the benefit is really being able to do the measurements with, or to get the information with a small amount of measurements. Is that correct?
That's right. That's right. That's the thing. I mean, when you are talking about aircraft, for example, this example was those specimen was in the fuselage of the airplane. Okay, so what you want to do after fabrication of those materials, you want to see if there is any defect or not. Okay, and this is actually the project was motivated by a problem. It was sponsored by Boeing. And that's actually what they do. So this is the guided wave test. But if you look at how the fuselages are being inspected, it's ultrasound, for example, and that would be location by location. Okay. So what do you want to do? You want to basically do dense sampling, or you want to increase basically the speed of sampling, or get the same information or similar information with a smaller number of samples. So that's in the inspection part. Another potential application, okay, of adaptive sampling that I didn't talk here is about simulation. So you guys, as you mentioned, that you're designing spacecraft components, and a lot of them require some design and some finite element simulations, some very expensive simulations. And you cannot run those simulations just freely, okay? So it's basically you only have a small a number of resources or computational resources or time. In terms of time, you only have a small amount of time. And what you want to do, you want to say, what would be the best settings that I can use to run the simulation and I can get most out of it, okay? This most out of it depends on what do you prefer. So for example, you want to have a surrogate model with the highest accuracy. That would be the definition of most out of it, okay? Because sometimes what you do, you run an expensive simulation set of simulation experiments, and then use that data to create a surrogate model, okay? And you want this surrogate model to be very accurate, for example. Then your sampling criteria would be based on accuracy of that surrogate model, okay? If you want another criteria, then you can define that. So basically the whole point is, when sampling is expensive, how you can make decision in terms of where to collect the next sample more intelligently and sequentially. Meaning that based on the information that I get from the previous samples up to now, what would be the best location for the next one? If I run my simulations, for example, for these settings, for 5 settings so far, what would be the best setting for the next iteration?
Yeah, that's great. Thank you.
Sure. I hope I answered your question, Glenn.
Yeah, I mean, that's good. It really, to me, it's like information theory, basically. How much information can you get per point or per simulation?
Exactly. I mean, and that's very interesting that you brought this up. Actually, one of the criterion that we use in active learning is entropy, which is a component of information theory. Yeah. Not in the one that I presented. We also have other works that we use entropy borrowed from information theory. Yeah.
How would you apply this to spacecraft? I mean, you talk about in aerospace, you have the fuse gauge, right? But on the spacecraft manufacturing, could you do the same thing?
So that's a good question. As I said, I'm not very familiar with that area, but I can tell you how it can be used in general. So let's say in your spacecraft, you have some components and you want to test those components you are designing, okay? And testing those components are expensive, okay? So you don't want to test like all the points, okay? All the locations. You want to make sure that based on the limited budget that you have, you can get most out of it. The example I gave you is coming from fuselage, okay? In the airplane fuselage, and the material that they are using is composite material, okay? So they use composite material in fuselage. And they want to know, based on some non-destructive test, whether there is a defect before assembly and after assembly. So before assembly is after when you do manufacture the composite sheets. You already manufactured that. Before doing assembly in the fuselage, you want to test that and see if there is any defect or not. And the tests that you are using, either ultrasound or guided wave tests, they are point-based tests, meaning that you cannot measure and see the biggest specimen at one point. You need to do it in point by point. And that would be a time-consuming process if you have a high throughput manufacturing. So what you want to do, you want to make it faster by doing this adaptive sampling. That's one example after manufacturing of your composite chip. The second one would be when you assemble that in the fuselage. Okay, again, I'm not expert. These are the things that I basically, when I spoke with aerospace engineers from here and there, and also Boeing, I learned. So when you basically assemble that composite material in the fuselage, what you want to do, you want also again do, for example, ultrasound, B scans, okay? And that one, you're talking about fuselage, which is really big. They do have big devices to do these tests. And again, it would be point-based, meaning that at each time, you can only inspect one small area, and then you need to move on to the next, okay? So instead of dense sampling, you can do adaptive sampling. That is one application, as I said, and another application was the answer I provided to Glenn about simulations. So if you have expensive simulation that you want to run, you cannot run it for so many different settings. For example, finite element analysis that you are doing, you cannot do it for so many different settings. You can just pick a few of them that gives you the most information that you can get.
Okay, yeah, thank you.
Sure. Any other questions?
I think it's a very interesting thing. I think we have to, for someone interested, we'll have to return to your lecture a couple of times to get
Sure.
the part of it.
The paper is available. I can share it with you if you cannot find it online. And to be honest, if you need any more information, or if you have any questions, I would be happy to talk to you about that.
Right. Yeah, I hope that some of the people, in the future would be able to get in touch with you to learn more about this.
Sure. We'll be happy to do that. So as I said at the beginning, my research is more on the machine learning and high dimensional data analysis. So the one I presented is basically since it had application in aerospace, that's why I kind of like picked that topic. But prognostics, I know that prognostics is an important problem in aerospace. This is one area that I work on. If you have data or if you have basically some problems in that area, I would be happy to talk to you about that as well.
I mean, we know that some researchers in Taiwan who are not here yet would be interested. So what we'll be doing is that like last time that Professor Steve Liang, and he gave a talk, and then we send this information, even this video link to a number of people, to tell them that please, this might be of interest to you. And in fact, some of them respond, saying that indeed they're interested. So I will do the same thing to your lecture. Thank you.
Sure.
So if there's no more questions, Grant, can you close the session?
Sure. Yeah, just thanks everybody for coming, and look forward to seeing you all next week.
Yeah.
Thank you all, and sorry about the delay again.
Yeah.
Oh, no problem. No problem.
Thank you. Enjoyed your talk.
Yeah, thank you.
Yeah, bye-bye.
Bye-bye. Thank you.
Yeah.
Bye-bye. Good morning and good evening.